was fast. However, even the fastest train on Earth, Shanghai Maglev, travels with the speed of 430 km per hour. For comparison, the speed of sound is 343 meters per second, which gives 1235 km per hour. And so far doesn't seem like any of our trains, the on-the-surface trains, will reach this barrier anytime soon. Well, of course, I'm not mentioning here the Hyperloop kind of trains, which actually make, at some point, reach this goal. However, planes do travel faster than the speed of sound, at least some of them. This is called a sonic boom. And when this happens and the plane starts traveling faster than the speed of sound, then an interesting thing happens, that first we see the plane and then we hear it. This is not the only phenomenon related to sound. Do you remember the train that a moment ago passed our screen very quickly? And have you noticed how it changed its sound as it was passing the observer? Well, it actually didn't generate a different kind of sound because it travels with the same speed as it passes an observer. However, a static observer perceives that sound differently as the train approaches and goes away. Now, this is called a Doppler effect, and Sheldon, please explain.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Yes, exactly. Thank you, Sheldon. Now, in the human words. The blue dot is source. For now, let's say it's a speaker. The red dot is an observer. Let's say it's you. Now, if both of them are not in motion and I start the animation, then the speaker generates acoustic waves which spread around. And these waves have the same wavelength in each direction. Now, if the source, let's say, will be a train this time or an ambulance, and it has some velocity, let's say it will have velocity of 161 meters per second, which will then move towards observer. Let's see what happens. We can see that the wavelength of the sound generated in front of that source is a lot shorter than behind it. Depending if the vehicle is getting closer to an observer or getting farther away, different wavelengths are reaching the observer, and thus a sound with a different pitch is heard. Now, if I use my stick to generate some waves, there we go. I think you can see that the wave in front of the stick has a lot higher frequency than the waves after the stick. Another interesting property of an acoustic wave is that it bounces from obstacles. So, for example, my hand is an obstacle, there is a sound wave traveling, then it bounces back and travels the other direction. This is used, for example, by bats for echolocation. They emit some kind of a sound, which then bounces from all the obstacles around, comes back to the bat, and then the bat can calculate how far it is from an obstacle not to crash into it. Now, this works in a similar way like a laser shot from a satellite towards Mars's surface, which we talked about in the first episode of Buffer Zone. If you don't know what you're talking about, just look into there. Sound waves have a variety of applications. Primarily, we use them for communication with each other. A human ear can typically hear sound with frequencies from 20 Hz to 20 kHz. This is so-called a human hearing range. Sound waves that are lower than 20 Hz are called infrasound, and they are heavily used in geology, for example to monitor earthquakes or volcanoes. On the other hand, sounds with frequencies above the human hearing range, so above 20,000 Hz, are called ultrasounds, and they are used in many ways in our daily life. For example, for monitoring pregnancy with ultrasound imaging, for echolocation, for object detection, and even for cleaning, for example, jewelry or camera lenses. How does it happen that I'm talking to you right now to this plastic microphone, and then in your present later on you can hear to my voice as I will be talking, well, right in front of your eyes? There are many ways to build a microphone, and this Wikipedia page will show you a couple of examples. And we will have a look at a dynamic microphone today. So first of all, microphones come in a different shape and different size, and here I have some microphones. So this recorder has two microphones on the top, which allows me to record stereo sound, as opposed to this lavalier microphone I have on my shirt right now, which will record just one channel, and then I have to propagate it to make two channels, which will sound exactly the same. This is a dynamic microphone, and this microphone has a membrane, which vibrates when a sound wave reaches it. Then this membrane is connected with a coil of, for example, copper. And this is set inside of a magnet, a circular magnet. So once the membrane starts vibrating, it moves the coil inside of a magnet, and this generates a magnetic and electromagnetic field, which then is transmitted as electrical signal into a device, whatever is on the other side of the cable. This is basically how a dynamic microphone works. A human ear is kind of a microphone embedded in a human body. And similarly to my recorder here, we have two ears, so we can record a stereo sound with both of our ears. Now, of course, human ears are not the best ears that there are in the animal kingdom, and there are many of animals which can hear a lot better than us. However, they still do a pretty good job, and the way they work is a lot more sophisticated, in my opinion at least, than how microphones work. So here I have some pictures of an inner ear, a middle ear, there is the outer ear here also. So first a sound comes to, well, this thing, whatever it was called, then the energy of that sound is gathered, and then some membrane vibrates inside of an ear, around here, eardrum. And this makes these three bones here vibrating as well. So this propagates the wave further into an inner ear this time. And in inner ear we have so-called basal membrane around here. So this is the snail, which also starts vibrating. However, different parts of this membrane are vibrating depending on what frequency the sound is. Then on this membrane we have a lot of so-called hairs, about 15,000 of them. Each hair is then connected to some nerve which will transmit a signal of which frequency sound reached the ear to the brain. And then the brain finally interprets this signal. So in a nutshell, our ears work exactly the same as microphones. They gather sound, the energy, and then they transmit this vibration, the vibration created out of a sound wave, into an electrical signal that can be understood by our brain. This video, which I linked also, serves a more detailed explanation of how the ear works, so if you're interested, check it out. Our ears are our microphones, but we also have a speaker right here. So how does a speaker work? Actually, it's very simple. So I have a couple of pictures over here, again printed out of Wikipedia. This is how a speaker looks like inside, but the basic concept is exactly the same like with a microphone. So for example, we can see there is also a coil of probably copper, there is some magnet around it, and there is some membrane which vibrates. The thing is that a microphone gathers a sound here and then propagates it down, and a speaker gets some signal from a device, for example, and then it generates these vibrations here. So it works in a reverse way of a microphone. Actually, if you ever played with a microphone and you ever plugged it into the wrong output, actually wrote to the output instead of input on some device, you could find out that a dynamic microphone could play a sound, like it would be a speaker.
To nie jest tak, że się boję głośno mówić o tym, czego chcę.
Gdyby tylko mieć pewność, że granica błędu za bardzo nie przesunie się. Human vocal cords work in a similar way as speaker does. They generate vibrations which compress the air and form a sound wave. However, there is an interesting phenomenon related to that. So when I'm talking, I hear myself differently than you are hearing me right now. And this is because the wave that I'm generating, it reaches your ear directly. However, when I'm talking, then I hear myself through the air as the wave travels, but also I am hearing myself through the vibration that goes through the bones in my skull to my ear. So in other words, I'm hearing myself twice. That's all I have for you today. The next time we will look into how brain perceives sound and into a couple other interesting topics, so give me a like and stay tuned.